Hello everyone, my name is Lisa. I'm speaking from the research center Simvestav in Mexico, and I will talk a bit about my current work parallelizing a texture description algorithm for breast lesion classification using OpenMP and CUDA. So breast cancer is the most common cancer in women worldwide. Early detection makes it possible for the patient to have the best chance for successful treatment. Recently, a texture description algorithm called Auto-Mutual Information, or AMI, gave the best performance results for breast tumor classification when compared to other texture analysis algorithms. However, the computational time required by it was also 12 times higher. Different imaging modalities are required for analyzing distinct types of breast tissue, for example, breast ultrasounds or the much larger mammograms. The average mammography size in the DDSM dataset is around 5,000 times 3,000 pixels per image. The AMI sequential version would take around 1.5 hours to run on such an image. In this diagram, we see the sequence of steps in the AMI algorithm. We have an input image which goes through a texture extraction technique to obtain a feature vector. The AMI algorithm focuses on the box section. When medical images are obtained, they are generally not under the same illumination conditions. We want to obtain the same feature vector for the same object. Ranklet transform, which is the first stage, helps us achieve this. Next, we use mutual information to obtain an element of the feature vector for each of the transformed images. Ranklet transform is a sliding window operation. This means we have a window of a certain size or resolution that covers a certain region of the image that we're currently considering. We compute a Ranklet coefficient for every pixel in the image, which replaces the middle pixel in the window, using the formula given above. Also, we consider different pixels in the window depending on the orientation under consideration, horizontal, vertical, or diagonal. This method is called Ranklet because we consider the relative rank of pixels within the window rather than their actual intensity value, making this method intensity invariant. In this diagram, we see how the window slides across the image from the top left to the bottom right. We note that the calculation of Ranklet coefficient is very computationally intensive since it is a per pixel operation. Also, we notice that they are independent of each other, since each window is covering a different portion of the image, which means we can compute the coefficients simultaneously. Next, after obtaining the several Ranklet transforms of a single image, we compute the mutual information of each transformed image. Mutual information measures the relationship between two random variables that are sampled simultaneously. In particular, it measures how much information is communicated on average in one random variable about another. How it translates to images is we have two images, and for a given position, we ask how many times do we see a value x happen in image 1 when a value y is in image 2. To keep this count, we build a joint histogram table. We can calculate horizontal and vertical mutual information features. On the right, we will see an example of an image with only 4 columns for the horizontal size. So, on the first iteration, we displace the image 1 column to the left, deleting the leftmost column, and 1 to the right, deleting the rightmost column. We obtain 2 images with 1 less column each. We calculate the mutual information for these images and say we obtain x as a result. We do the same process and we are left with 2 images with 2 columns. We compute their mutual information. On the final iteration, we remain with a single column. We note that every one of these mutual information computations can be done independently, although that means computing a separate joint probability table every time, which doesn't vary too much from one iteration to the next. For datasets, we used 4 sets of squared images composed of the regions of interest obtained from mammograms. The regions of interests are of size 128, 256, 512, and 1024 pixels per side. Each of the four sets contained 100 images for a total of 400 images. For the equipment, we used two Xeon processors with 6 cores each, and also 3 different Tesla C2070 NVIDIA graphics cards. So for the OpenMP implementation, we achieved a speedup of 8 to 10 times. The graph shows the execution times for the AMI for different sized images. As expected, we see that the larger the image, the greater is the execution time. However, the OpenMP execution time increases at a lower rate. Here, the 1024 side image only takes around 3 minutes to compute with sequential C++ program. However, following this trend, the next power of 2 image of 2048 pixels will take close to half an hour. Here we see the speedup to C++ sequential code for all window and image sizes in the dataset. We did not completely obtain the trend we expected. On one side, we expect that for a larger Ranklet window, we get more speedup, which was in fact the case. However, we would also expect the speedup to increase with ascending image size, which didn't happen. The greatest speedup was for images of size 256. I attribute this to the fact that we are using two Xeon processors, and for these measurements, we used 12 threads. This means that the two sockets were communicating and the inter-socket bandwidth is about 5 gigabytes per second. This may have introduced this unexpected trend, not to mention the unpredictability of thread behavior. Here we see the speed up to C++ sequential code for different thread scheduling types for the Ranklet on the left and for the AMI on the right. For static scheduling, OpenMP divides the iterations into chunks of chunk size, distributing the chunks to threads in a round-robin fashion. If no chunk size is specified, the iterations are divided equally among threads, and each thread gets at most one chunk. On the other hand, in the dynamic scheduling, each thread executes a chunk-sized chunk of iterations, and when it has finished, requests another chunk until there are no more chunks to work on. From how the algorithm is designed, I would expect static scheduling to outperform the others during the Ranklet transform, since it is the best for regular tasks, meaning that each iteration of the loop takes the same time. An interesting secondary measurement would be using a single Xeon processor, where I would expect the dynamic scheduling to be outperformed by the static. Dynamic scheduling, on the other hand, would be best for irregular tasks, which means that your iterations may have different execution time. This is useful because a thread can process multiple small tasks while another can process less, longer tasks. This seems consistent with the graph on the right because of the fact that computing AMI for the different iterations takes a very different amount of time, since we're doing per pixel counts to fill up a joint histogram table on different sized sub-images. So, in CUDA, threads are grouped into thread blocks. Threads of the same block have access to shared memory, and their execution can be synchronized to coordinate memory accesses. We can have at most 1024 threads in a block. Thread blocks must execute independently, that is, the computations carried out in one thread block should not depend on the computations outside of that thread block. Looking at the diagram of our algorithm on the right, depending on the orientation and resolution selection, we will obtain a Ranklet transformed image. Since we're using 4 window resolutions, we obtain 12 images. For each of these images, we compute its horizontal and vertical mutual information features to obtain 12 times 2, so 24 features. Now, what we're parallelizing again are the windows in the Ranklet coefficient calculations and the sliding in the AMI stage. For an image of 1024 times 1024 pixels, since we can have 1024 threads maximum per block, we can have a block compute an entire row or column of the transformed image. For mutual information, we're parallelizing the sliding windows. This means that for every column in the image, we are filling up a table of int of size 256 times 256 simultaneously. Clearly, this can be a problem. This could maybe fit in our global memory, but we generally want to minimize global memory accesses, since this is the memory with the slowest access. What we could do is use share memory, but we already see that this will be a problem since our table would not fit in 48 kilobytes. We need to find a different strategy for the mutual information section, like filling up chunks of the joint table that will be in shared memory and keeping all intermediate quantities in device to avoid unnecessary device to host overhead. A hybrid strategy would use up all 3 Tesla cards we have, assigning roughly the same amount of workload to each. In our particular example, we would compute all the horizontal Ranklet transforms in one card and the diagonal and vertical ones in the 2 other cards. We still would have the same instruction level parallelism that we had in CUDA. So, in the results so far, OpenMP gave a maximum speedup of 10 times to the C++ sequential version. The performance improvement was only 1.3 times for the Ranklet transform, but 8 times for the mutual information. The best thread scheduling type for both stages was dynamic, and we're planning on doing a hybrid implementation that will parallelize tasks in OpenMP and instructions in CUDA, using all resources available in the system it is running. Considering an m times m sized image, we can optimistically expect our future implementation to improve the Ranklet transform by a factor of m squared, and the AMI by a factor of 6 times the number of resolutions times m. So that's all there is to this work so far. It is still under progress, so if you have any questions or suggestions that can be made, I hope to hear them in the poster session. Thanks for watching.